we should have done that. Yeah. So let's do a problem which is, so let's do a slightly challenging question. Okay, today to begin with, and this is under the theme called monovariance. It's kind of invariant, but it's a, let's just do it through a problem. Okay. So we have two groups. Okay. Two groups of people. Two groups of people. So we have group A, group B. Okay. And some number of people, that number is not given. Okay. Or maybe in this case, I can give you, okay, two groups of people, each with 10 members. Okay. Each person has at most, let me just confirm. I think it's 3, but yeah. So each person has at most, sorry. So there is no, I don't need to say groups of people initially. So I'll just say it like this. Sorry, just changing it. Okay. So we have 10 people. Okay. Each person has at most 3 enemies. Okay, so that's the number, 3 enemies. Okay. What we want to do is we want to divide the people into 2 groups so that there is peace. So show that it is possible to divide them into 2 groups, okay, into 2 groups, so that each person has at most 1 enemy, okay, has at most 1 enemy in his own group, because obviously overall that number, if he has 3 enemies, that's not going to certainly change, right? But in the group he is in, he will have at most 1 enemy in his group. Okay. So this problem is example. It's an example 4. It's example 4 in Arthur Angel. Okay. It's some old question. So yeah. Yes. Yeah. Yes, I think that's fine. Yeah. So if one has enemies 2, 3, and 4, then yeah. So we can say that 2. Yeah. If one is an enemy of 2, one is an enemy of 3, and one is an enemy of 4. Yeah. So that's enmity goes both ways. It's a symmetric relation. Yeah. Yes, certainly. So let us just, I'll name the people like this. Yeah. Just think. And these are again small puzzles, but they become theorems later on in graph theory. No, they don't have to be. Yes, exactly. Yeah, at most is just the maximum, but I mean, yeah, at most. Yeah, it's very good if he has 0 enemies in his group. Yes, but the point is that we cannot decide who is enemy of whom. Right. I mean, otherwise you can just Otherwise you can just create a I mean, otherwise you can say that nobody has enemies of anyone initially because it's at most 3. Yeah, but I see you're trying to construct a case in which everybody has 3 enemies, but still you have a But yeah, you cannot decide the you have to show that in any situation it can be done. Sorry. If he has 3 enemies. No. Why? No, if one has enemies with 2, 3, and 4, then what's wrong with 2 and 3 being in the same group? This is not a problem. 2 and 3 can be in the same group. In fact, 1 and 2 can be in the same group because so it's a very interesting question because now you see now we can understand through our small observations and wrong observations and right ones both, that in any situation we have to show that this can be done. Okay, and that's the thing about maths, right? We're trying to prove things which apply to as many situations as possible, or all situations, with some assumptions. This is the thing about maths and theorems, proving things about many things at the same time. I mean, otherwise, if some specific situation is given, then you can possibly just do it by hand, or develop some method. Yeah. And I am too lazy to maybe draw 10 people and construct an example. You can try to do that. I'm not doing that because it may not, I don't know, may not be useful, I feel. Yeah, so it's difficult to, maybe if you have never done a question like this, then it's a little strange. But so essentially, see, we have 10 points, right? We have 10 points, right? And one person has at most 3 enemies. Like this maybe. And so this person may have 3 enemies, and so on. How would you separate? How would you group them? So the way we will do this problem, so I'll just give some small hint, is we will start with the 10 people and just one group. Okay. And then we will just try to go naively in the sense that we will try to decrease the number of enemies someone has in the group, in the sense that if we find that someone has 3 enemies in his own group, then we will just move one of the enemies to the other group. Okay, as simple as that. So we are just going to do the simplest thing possible, right? That will be the simplest thing possible, right? So initially you have these 10 people in one group, just 10 people, right? Now, if P1, let's say, has enemies with P3, so maybe so let's number it a little bit. So P1, P2, P3, P4, P5, P6, and so on. So let's say that P1 has enemies with P2, P3, and P5. Okay, then we will just move. Then what should we do? I mean, what's the natural reaction, right? You would say, okay, P2 or to P3 or to P2, you please go to the other group. Or you can just take P1 to the other group. It doesn't, but it doesn't matter. That's the point. Okay, so if someone has 3 enemies, or rather, I don't take P1, or I mean, yeah, but let's see. So simple one way to do this is like if P2, so P2 is one of the enemies, right? So this guy has 3 enemies. So P2 is one of the enemies, right? So we move P2 to the other group. This is the simplest thing, right? All right. So that does not work, right? No, I mean, so yeah, see, the problem with removing P1 is that you don't know about P2, P3, and P5, right? But no, see, our ultimate goal is that to make that a person has at most one enemy in his group, right? So if someone has more than one enemy in his group, then no. So should I move? So the question is, should I move P1? Should I move P2, P3? 1 minute. Let's just think. Yeah. Yeah, we don't know the connection between the other two. That's the point. But also, then we will know that P1 will not have any enemies in the other group, right? But that also seems to be too good in the sense that it will not then overall work, right? I mean, this kind of strategy will overall not work, right? Because you can never get such a situation like everybody like they don't have any enemy in their own group. That seems too good, right? Like it shouldn't be possible that that happens for everyone. Yeah. So let's just move P2 and P3 to the other group, or I'll just say that if someone has more than one enemy in his group, then move one of the enemies to the other group. Okay, so following this, at one step we're just going to move P2 to the other group. Okay, And obviously then later on you will move P3 also. But in each step we are going to do this. Okay. And then in the next step also maybe we'll move P3 or P5 to the other group. Is it okay? So this is what we're going to do, but it's not obvious at all that this will eventually give us what we want. So is a step clear what I am doing? That if someone has more than one, because we don't want more than one enemy in a group for anyone. If someone has more than one enemy in a group, then you move those enemies, or move one of the enemies to the other group, and if you keep doing it, then you'll move both. Yeah. But then if you keep doing this, then why should it eventually give you the partition, so that in their own group they don't have. Yeah, it's at most 3. So yes, they can be enemies, or they may have enemies, like they may be having enemies here. That can also happen. Yeah, they may be enemies, or they may be having. So does this help us? That is a thing. You can see that this does not help us, right? Yeah, and not just it's messy, but more than that, it is a cyclic thing. It's a cyclic problem, in the sense that you had P2 and P3 here, and that made P1 had 3 enemies here, and so we moved these 2 guys here, but they could have be enemies. They can have enemies with P10, but now what will you do, right? Now, I mean, if we follow this algorithm, then it's possible and it's legal, it's legal to make P2 move back, right? Because P10 now has 2 enemies, so it'll move one of the enemies back without any discrimination, just randomly. So you move P2 back, right? But then when you find the P2 here, you move the P2 back to this group, the right group, but then you end up in a cycle. Right. If you just execute it like this without any more restrictions, then you just keep moving it back and forth. It doesn't seem to, yeah. It won't help at right, because you have to move one of P2 or P5, and then P1 will end up. So this will just not work. So it's not just messy, it will not work. So does everybody see why this does not work? Okay. Yeah. Like, because because you have to move P2 or P5 that to the other side, and then you will increase, and then you'll come back, but this doesn't just mess. It doesn't work. So then we have to change. We have to do something else. So what should we do? We have to do something similar, but not this. So you see, in fact, so what we were thinking earlier, in fact, that is the better thing to do. Okay. And that is to move P1 So we would want to move P1 to the other group. Okay. So if someone has two or more, rather just two or three enemies in his group, then it is just wise for him to move to the other group. And that's the best thing, best thing to do, right? Then he moves to the other. Actually, in fact, these kind of simple logic of just common logic actually works in a lot of cases. Okay. Yes. Obviously, sometimes this is counterintuitive, but yeah, then he moves to the other group. He just walks, he just changes his group. That's the wise thing to do. So he has problems with three people, or let's just take two people. It doesn't matter, but let's keep three. Okay, so P2, P3, and P5. Then he just moves to the other group. So then we will move P1 to the other group. So this will give us P1 here. And so why will this work? Huh? Yeah, so it's fine. At most one means it can be zero also, right? At most one means it could be zero also. So for the just to take another example, suppose P4 has enemies with two people, then now it means that P4 has an enemy in this group. So it could be P9. Right? But that's fine. That's only one enemy. Okay. So it's wise for him to move to that group. It's just better for him to move to the other group. So then that's what he does. He just goes to the other group. Yes, that is certainly possible. That P2 has enemies with P3 and P5. And then, yes, so in the sense that P2 moves to this group, then you find that they are back, the enemies are back, but that's fine. We just have one enemy. Yeah, but this is by no means a proof of anything. It's just something that once you think of this good logic, seems like a good logic, try it, or just make 5 people and just make an actual graph, and you just do this and you see it works. But how do we prove this? That this will eventually give us, yeah, how to show eventually means after some number of steps. We don't know how many steps. Okay? The desired grouping. So you understand what that means. So how would we reason it? Mm-hmm. But then, so initially, how can you assume that two people don't have any enemies? That's okay. See, if you assume that, then it works. But then it's just like taking 8 people, right? Uh, right. But in general, it has to work. Like, yeah, I mean that's a very easy. That assumption makes it easy, but that assumption is very special. That two people don't have enemies at all. So I mean, you could still make it work. Like, so there are 10 people, the 3 enemies. You can take 3 enemies for everyone and try to make a graph, and then try to do it. Okay, but I mean, yeah. Let me show one situation where it seems like this is a little tricky, because what if the situation is like this? So we're trying to advocate against this, and we'll see that we cannot. But so let's say this P1 has enemies with P2 and P3. Okay, and let's say that this P2, so these are the enemies, and now it could happen that P2 and P4, P5, and this also has enemies with maybe P6 and P7. Okay, then you see in this case, if you initially move P1 to this side, then you feel it's good because, yeah. But then P2 and P3 also have 2 enemies each in their group in which they are. So you have to move P2 and P3 also to this side. Is that okay? So the situation, okay, it doesn't become the same, but obviously now you will have to move the P1 back and then everything is good. Okay, or in the worst case, P1 could have 1 enemy more in this group, in that group again, if he had 3 in the beginning. Okay, so then you would have to move, but this is what you have to do. You would have to move P1 back. And now it cannot have more than 1 enemy here. By our assumption, it doesn't have any. If it initially had 2. So you may have to move one guy, not once, but twice. Okay, so be careful. Okay, so you may have to move, I mean, you may have to move one person, not once, but twice. That's the point. Right? So then how do we show that it works? Can you prove that after a person moves twice, then he doesn't have to move anymore? If you can show that kind of thing, then you are done. Is you guys agree? Yeah. Yeah. So the point is, so can anybody explain what I just said? Why that will be good? See, if you come to a situation where you don't have to move anyone, then job is done, right? Okay, so that's an easy assumption, easy thing, right? If we don't, if no moves can be made, yeah. So if no moves, uh, can be made, then done. You can go home. Everybody gets this, right? Because no moves can be made means that every person has at most one. Yeah. So you have to come to a place where no moves can be made. So from what we are seeing, it seems like, so from what we are seeing, like initially you could have said something like, okay, once we move the person to that group is done. Then similarly you do for everyone. Then there are 10 people, after 10 moves you don't have to do, but that's wrong because one person, as we saw in an example, may have to move twice. But then the claim is that maybe you can try to show that a person maybe doesn't have to, cannot be moved more than 2 times. I don't know if that is true. Is that true? Can you reason that any person right? Yes. Yes, yeah, that seems like a that seems like a reasonable assumption. That's reasonable thing. Does everybody agree with that argument? Yeah. That yeah. So what he's saying is that looks initially if someone had three enemies, yeah, then if initially someone had three enemies in his group, then you would have moved this person to the other group. Let's do the case where someone had three enemies in his group. Then the two enemies we can do. Then you move this person here. Okay. Now, if you are having to move this person back again, it means that it means that it means that these two people or two of those people have landed up here. That's why we are moving that person back to his group, his original group. Now this person has at most one enemy is in his group. He has, let's say, exactly one enemy in his group. Okay. So now we will. So now what Unab said is that now we don't need to move this person anymore. So does everybody agree with that? Okay. But is there a fault in that? Because what could happen is that these two people who are in this, who have moved here, they could they not move back at some point? No. Yeah. So, but why? But we have to explain why that cannot happen. Is it clear that that cannot happen? See, it seems difficult to explain. Or, sorry? No. You don't, because some other enemies could have come to this group after some point, right? So they moved here thinking that they would get rid of, they would not have to meet some people, but then these people, these were enemies, but then these people ended up here somehow, and then they have to move back, and then they are playing chasing it. I don't know, right? It's complicated. You see, it's a little messy. It will not eventually happen. Eventually, it will not happen, but it seems strange. So this claim, though it looked correct in the beginning, it doesn't seem. No, so I'm doing all this just exploration, or maybe I don't know if it's useful or not. You guys can tell me if I should cut it short. Try to. I don't know, but yeah. Yes, exactly. So that's the fear, right? That is a fear. That's what I'm saying. Yeah. And unless we explain why that cannot happen, it can happen. Maybe. Yeah. I mean, any person cannot move more than twice. This we thought it is correct, but it is now there is a big question mark. No, because no, but they don't care about P1, right? In the sense that when they move, so let's say that this is P8 and P9. So P8 and P9 move here, right? So they move here not for P1. Right? I mean, when someone moves to a different group, it's because they are trying to avoid the enemies in their own present group. Right? They are trying to avoid the immediate threats. Right. And they move to the other group. So they don't care, or maybe they don't know, or they cannot care about that or enemy in the other group at that point. Right. That's not in the algorithm, right? It is this step. So that's the problem. Yeah, because let's imagine, so like this P8 could have these enemies. P8 could have enemies P4 and P5, and P9 could have enemies P6 and P7. So let's forget about this first. So let's say that point is it's getting extremely messy. And that's where we will see that invariance principle will give us a very simple proof, a very, very simple proof. Okay. We have to set up our invariant, but we'll see that. So the point here is that P3. So point is that this P1 first moves. So let's try to imagine, like, is there a situation in which we could have 3 moves? Then how would that situation look like? A situation in which P1 would need to make 3 moves. Okay, let's see if we can make such a situation, right? Then all this argument we don't need to do. Then we can just say. So this P1 moves here, and that's fine. Yeah. But then this P8 and P9 also move. Okay, P8 and P9 also move to this group. So let's not write all these things now. Yeah, and the moment P8 and P9 move here, the P1 moves back. Is it fine? The P1 moves back. So I'm just saying it in words because I cannot draw everything. The P1 moves back to group 1. But then what happens is the P4 and P5, yeah. So let's say that the P4 and P5 have 2 more enemies in their own group. It could be more than 10 numbers, right? Your problem is true for more than 10. And let's say that all of these had, so I see it needs more than 10, but just bear with me. So 10, let's say that this is the situation. Okay. Then what would happen? Then the P4, P5, P6, P7 all would need to move to the second group. Do you guys agree? Each have 2 enemies in their group. All need to move to this. But then when this happens, then this P8 and P9 will run away again, or rather they will choose to go back to. It's a very strange thing, but this, I don't know. This is what's happening, right? So this P8 and P9, then, okay, so I should have removed it for a moment, but then they come back. When this happens, that they come back, but then the P1 has to move back again. They have to move to group 2, not move back, I should say. Just that then they go to this one, right? But then P1 has a problem, so he comes here. And you may say 3 moves, but then I'll say no. You see, so I don't know. So how do you reason this? You see, I mean, this is interesting because we are able to actually make the examples. Okay, so let's not get into this in that way. Okay, so we will, after we prove that this can be that this process does work, after that we can ask some interesting questions. Okay, but now we should first do this. Okay, so what should be the invariant? Okay, so now let's clear everything and let's think about the basics. So is this I mean, is this yeah, everybody following this? Yeah, Pragdish. Yeah. Okay. So you see, all this, so this may seem a little too long stretched out, but I don't know. So you guys have to see feedback from you guys, but I can tell you that these kind of things are interesting. Okay, for you to catch up and do more on this things, and these are the arguments you will need later when you do more interesting questions. But okay, So, yeah, but for the purpose of this problem, this is probably not necessary. But just to see. So invariance principle helps you to formalize intuition. And so that's the point. So, so now back to the thing. So can anybody tell the basic algorithm that we had suggested in the beginning? So that I can write that again and then we can reason. So I would like someone to say the basic algorithm, because yeah, it is an algorithm, right? It is a few steps that we had to do. So it was simple. Please, someone say. Anyone, just go. Don't wait for the others. Just say. Someone just. Yes. So initially for this problem, we suggested an algorithm, right? Which so what is that? Which we think will work, but we have not proved it. So what was the technique for us to get to the place where everybody has at most one enemy in their group? No, the common, yeah. So I mean that if someone has more than one enemy in their group, then they move to the other group. Okay, this one, because see, the one before that clearly did not work. That we even saw that it cannot work. Right, the one that I suggested initially, we saw that it doesn't work. But then this one, which is a better algorithm for you, just even if you think just no purely, this is better, right? So the algorithm is that if some person, if pi has more than one enemy in his group, then he moves to the other group. I mean, this is really an algorithm, right? You could even code this up if you guys know coding, which I have forgotten, so don't ask me. Okay, and it's because I'm not, I don't do all that, but it's very simple. But the point is, you can even code this up. Okay, so you can create a graph, you can create these pairs of, you can create an array of pairs where these pairs are enemies, and someone maybe should do it, and you would see that after how many steps it gives the answer or whatever. I mean, you take a large number and you see the time ratio, whatever you guys do, you can understand then, right? And you can see that this will stop, and this will give you the, yeah, because you can give that condition of stopping. This is there. So if pi has more than one enemy in his group, then he moves to the other group. This is just the logically right thing to do. But then mathematically, we are not able to prove the termination of this algorithm. You can treat it like that. Okay, mathematically, we want to show that this stops, in the sense that you come to a stage where no one has more than one enemy in his group. Okay, in the group. So how do we show the termination? Okay, so basically what we're going to do is we're going to construct a quantity, just like in the sum problems we had the sum of the numbers on the board, or some number of steps, number of pieces that was going down or that was constant. You guys see, right? We have to construct some quantity and we want to show that it goes down. What should that quantity be? So we will make an invariant, or it will be a monovariant, but what should that quantity be? Is everybody following? Like where we are, how much we have done, and what we need to do? Okay. Something, yeah, some global thing which will be fixed or which will change in a certain controlled way, whatever. What is a natural thing to think about? So we would have to, because see, we want to bring down the number of enemies someone has in their group, right? Someone has in their own group, not total number of enemies. Total number of enemies doesn't change. Yeah. So what should the quantity be? We will take the sum of the total number of enemies that someone has in their own group, right? So yeah, so that will be the sum of number of enemies of people in their own group. Huh? We have to, yeah, we have to do it over all the people. Okay, so if we take a small example, yeah, let's take, not, I won't take 10 people, just take these 7 people only. And so we have all the 7 people, all 7. So let's see. So in this case, what will that number be? So you see, let's say that P1 has enemies with these 3, with those 2, and let's say that this is full of enmity. Okay, this is the best maybe, or yeah, let's say this is full. Okay, right? So then what is this number going to be? Let's see. Okay, so someone can tell me what, I mean, just this by the steps. I don't want the final answer, that's not important. But how would you compute this quantity for this particular case? For this particular case, what is the total enmity that people have in their own groups? That is important. So yeah, so let's do it. For P1, there are 2 enemies in this group. For P1, there are 2 enemies in his group. Fine. We have to go to P2 also. P2 and ask him. He says, I have 1 enemy in my group. P3 has 1 enemy in his group. See, as I'm repeating this again, P3 could have another enemy. Well, it won't have because now there are 3 already, but just saying, P3 could have some enemy in the other group, but that is not important. Okay. So it's 4 plus, and just again, if you just count, so P7 has 3, or rather P4 has 3 in his group, P5 has 3, and similarly. So this is the initial quantity. So is this clear? What is this quantity? It's a slightly complicated question, but I just wanted to show this thing. Okay, so Pragadish, do you also see this? This because this is a new quantity. This is the new that we have created. Okay, yeah. So this is the thing. So this is the quantity that we are creating. What do we want to show about this quantity? So this quantity is the total enmity that people have in their own groups. Okay, in their own groups, in the total sum enmity. We want to, so we don't want to show that this is constant, right? We don't want to do that, right? I mean, if it is constant, then how will you conclude that you are done? Right. See, we want to show that you will come to a place where people don't have any enemies. Sorry, you want to come to a place where, someone that you want to come to a place where person doesn't have more than 1 enemy in his group, right? You want to come to that good place. So then you would like to show that this quantity goes down at each step. Okay. Yeah. So we want to, so if we call this I, well, this is a function and so on, but let's I, right? So we want to show that I reduces at each step. See, it may reduce by 1, by 2, but it reduces. That is the key. You will have to show that I reduces at each step. Okay, so try this out. Try to show that I reduces. Okay, so it's not very difficult, but you will have to try it first. Okay, so once you show that I reduces at each step, okay, well, what does that mean, right? So at some step I can become 0, but then after that it cannot reduce any further. But then what does that mean? Well, it means that you cannot really go further. It means that you have to stop. Right? So it would mean that the algorithm has to stop. Does everybody see that? If you show that I reduces at each step, because I may be 1000, okay, but if it reduces at each step, then after 1000 steps, I becomes 0. Well, once that happens, then certainly you cannot move forward. Right? Then there, I mean, even before the algorithm will stop in practice, but that is certainly a place where it cannot go further. Yeah, I mean, if it's 1, then it's very good, right? But the point is that I always reduces at each step. That's what you have to prove. So it will not reduce by 1, but you have to show that if there is more than one enemy, so if there is someone who has more than one enemy in that group, okay, then making a move, I will reduce. But I cannot keep reducing. Right. It's a natural number. Right. So like if P1 has 2 enemies in his group, and let's say he has another enemy, some P10 in the other group, then when you move P1 to the other group, then what happens? Let's see. When you move P1 to the other group, then for P1, the number of, so let's say the I was the I, some I, then for P1, the number of enemies have reduced by 2, okay, in his group, but then it may have increased by 1 in the worst case. Yeah. If it doesn't, then it's very good. May have increased by 1. Okay. What is happening? See, for P10 also, his one enemy may have increased. Is that right? Yeah. For P10 also, he has attained a new enemy, right? And okay, but then so for okay, so let's do it again. So it's more than 2 actually. So these 2, I think, so it certainly reduces by 2 because P1 loses 2 enemies, right? P1, yeah. So so the number of enemies of P1 reduces by 2 and it at most increases by 1. But there is more good news. What is that? That P2 and P3 also get rid of 2 enemies, right? So that's again -1, -1, right? But then when P1 comes here, then P10 gains an enemy maybe. If P10 is so P10 gains an enemy. But nothing more can happen. No other changes can happen, right? And you can see that this quantity is -1 at least, right? So -1, whatever, you can check that. Yeah, it's -2 actually. So very good. Reduces by 2. So I goes to I -2. So initially we had I number of enemies, and then that goes to I -2. So forget about this Y. In each move, you see, so yeah, someone gains an enemy, someone loses an enemy, all that is fine. But this total number is a good thing that that number is reducing. Right? So this number, for example, this number would become reduced by 2. Okay, so if someone has more than one enemy in his group, then this number will reduce. But this number cannot keep reducing, right? So it means that at some point, nobody has more than one enemy in their group. Yeah, so this it's not that this number is not increasing. That's not enough. This number has to reduce. That is important. Okay, so now is it clear to everyone? Yeah. Please see if you have any questions. Ask me. Then we won't do anything more. So you can just check. So Pragdish, Nagesh, everybody, just see if there is this. Go through it and see if there is something which you want to ask. I'll leave this open for some time, maybe like 5 minutes, and then you can